Two scientists from Stevens Institute of Technology in the United States developed a mathematical model explaining how the famous wave-particle duality observed in the double-slit experiment emerges, and their work was published in a prestigious journal. But it didn't stop there. They experimentally confirmed the model they had built. What does this mean? It represents a potential breakthrough in fields such as quantum computing, medical imaging techniques, and quantum radar. One point to highlight: you're likely to see this paper everywhere in the coming days. We wanted to be the first to cover it. At this point, we kindly ask for your support. If you like and share our video, it would be a great help for us. While the video has just started, I would like to make one thing clear. Science, unlike philosophy, often seeks answers to the question how rather than why. So, in this video, you won't find answers like, does quantum matter have consciousness? Or, why does the wave in the double-slit experiment collapse into a particle when there is an observer? Instead, you will get the answer to this happens. Until now, no one had been able to clearly express exactly where wave-particle duality begins, where it ends, and in what proportion a system exhibits wave-like or particle-like behavior, using a simple and clear equation. What these scientists accomplished in this paper is precisely that they placed the phenomenon into a well-defined mathematical model. As a result, we may now have a strong answer to the how question that has remained unresolved for nearly 80 years. Let's first clarify our position. A photon can exhibit either wave-like or particle-like properties, but it cannot do both equally at the same time. In other words, a photon cannot behave as 50% wave and 50% particle simultaneously. Under specific measurement conditions, a photon undergoes a transformation and behaves either more like a wave or more like a particle. This phenomenon is often explained by Bohr's principle of complementarity. However, until now, mathematical approaches have not been able to fully express this behavior quantitatively and could only impose one limitation. The square of the wave property plus the square of the particle property must be less than or equal to 1. This situation sometimes led to ambiguities, making it seem as though both properties increased at the same time. For us science enthusiasts, that was all the picture had been for a long time. Yet there was a significant gap between what truly happens and the mathematics used to explain it. This is exactly where the paper comes in. By introducing an additional factor called coherence, they established a more precise relationship, presenting a new mathematical model that clearly defines the combined behavior of wave and particle properties. And this isn't just a theoretical curiosity. This new approach can be directly applied to practical technologies such as quantum imaging with undetected photons. So what does imaging with undetected photons mean? Normally, to obtain an image of an object, the light that strikes it must be detected. In other words, the photons are expected to reach an imaging sensor and be measured. However, in this study, the information forming the image comes not from the photon that directly interacted with the object, but from its entangled partner photon. This means the image is reconstructed from a photon that never even touched the object. That is a truly fascinating approach. Physicists at Stevens Institute of Technology noticed that existing approaches explaining wave-particle duality were missing an important element: phase coherence. Coherence describes how well a quantum particle's two possible paths remain in sync, meaning how well their phases are preserved. By two different paths, think of the two optical paths a photon can take in a Mach Zinder interferometer. If the phase difference between these two paths remains constant and there are no disruptive effects such as vibrations, temperature changes, or random photon scattering, the system exhibits perfect coherence and produces a clear interference pattern, meaning the photon behaves entirely like a wave. To make this more tangible, imagine two bowling balls released side by side in parallel lanes at the same time, with the same speed and the same angle. If nothing interferes with them, they roll in perfect harmony and reach their targets together. This is what scientists refer to as the fully coherent state, where the wave property is perfectly preserved. But if you try to measure the speed or position of one of those balls, you disturb the system, altering their trajectories and the harmony between them. In the quantum world, this is like changing the phase difference between two paths. The greater the phase difference, the weaker the photon's wave property becomes, and the interference patterns begin to fade. Once this process crosses a certain threshold, the system effectively chooses only one path, and the photon behaves solely like a particle. What the scientists emphasize is that this transition fundamentally depends on the change in phase difference between the possible paths of the photons. To understand this, scientists first re-examined the existing mathematical framework. The classical approach used to describe wave and particle properties only defined one boundary. The square of the wave property plus the square of the particle property must be less than or equal to 1. However, this expression was incomplete because it did not directly take into account the phase alignment between the two paths, in other words, coherence. The researchers addressed this gap by explicitly adding coherence into the formula and reached the following conclusion. The relationship between wave and particle properties can be described precisely with an elliptical equation. This new equation clearly shows how coherence determines the balance between wave-like and particle-like behaviors. After establishing this new mathematical framework, the scientists tested their model in a real quantum imaging experiment. You might wonder how such a technical and complex idea could possibly be tested. Get ready, because this is one of the most ingenious and challenging experiments in recent years. First, light from a single laser source was split into two beams using a special beam splitter. Each of these beams was directed into a nonlinear crystal, known as NL1 and NL2. These crystals converted the light into two separate pairs of photons with the property of quantum entanglement. One of these pairs, known as the idler photons, was directed toward a semi-transparent object, in this case, an S-shaped mask used in study. Interestingly, these photons were never detected by any sensor. Their only role was to carry information about how much light the object transmitted and how much it changed the phase of that light. This interaction with the object created a phase difference that was then transferred through quantum entanglement to the other photon pair. The other pair, known as the signal photons, was placed in a superposition. This ensured that the phase difference introduced through entanglement was applied to at least one photon. These two paths were then recombined using a beam splitter, and the resulting interference pattern, created solely by the combined signal photons, was measured with highly sensitive detectors. The clarity of this pattern was compared to a reference interference visibility obtained when no object was present, that is, when the idler photons traveled through empty space. The results were striking. When there was no object, the interference pattern exhibited perfect wave-like behavior. But when the object was introduced into the system, meaning the photons experienced a phase difference, the interference pattern gradually faded and eventually disappeared entirely. In other words, the greater the phase difference between the two paths, the weaker the interference pattern became. This finding clarifies a long-known result from the double-slit experiment. Obtaining information about which path a photon takes disrupts the coherence of the system, destroying its wave property and forcing it to behave like a particle. In short, simply gaining knowledge about the path changes the phase difference and transforms the photon from a wave into a particle. The essence is this. A strong answer has now been given to a question asked for 80 years. How does a photon transform from a wave into a particle? Moreover, this answer holds great potential for the advancement of quantum technologies. A model that mathematically determines exactly when and how a wave collapses into a particle could spark a breakthrough in fields like quantum medical imaging, quantum radar, and quantum computing, comparable to the transistor revolution. Thank you for watching.